She was.
Oh, yeah, she called him dude.
What was he? Wait.
Okay, so that shows more than one thing.
I have to touch myself.
Okay.
What about Cook Cat?
Good morning, ladies and gentlemen. How are we doing today? Quick, name me something about one of the scientists we talked about yesterday.
Avogadro mole.
Avogadro gives the concept of the mole. Good, go. I don't care. Come on, let's go. The sooner we get this done, the sooner we get to our stuff today, the more time we have to work the worksheet. Thompson found the electron. Good. 90 degree. What do you got? Newlands.
Law of octaves.
Law of octaves. Yes, very good, very good, very good. JPP.
Thompson gave us the plum pudding model.
Correct. Good, 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 good. Achilles. Rutherford found the nucleus. Good, 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 good. Well, that sucks. Now we're out of all the ideas.
Bohr gave us electrons and energy levels.
Bohr gave us electrons and energy levels, or he called it a quantized electron. Who gave us quantum numbers?
Oh,
Who's the guy you'd like to go beat the living snot out of?
Planck.
Planck gave us quantum numbers. Very good, very good, very good. Who found who found the alkali metals? Davy. Good. What did Berzelius do?
Atomic mass?
Relative
Atomic masses of the metals. Okay. Oil drop experiment.
Milky Man.
Millikan.
No.
Millikan. Law of definite proportions.
Proust.
Proust. Good, but not what I'm going to ask you on a test. What else did he do?
From the building block of all elements.
Conservation of mass.
Yes, and by the way, he did not cut his own head off. He had someone else do it for him.
Yeah, he got
Okay, had someone else do it for him. Einstein.
Einstein, you.
Okay. What did Einstein do?
He was a funny guy.
He was a smart, funny dude. Had a comedy show on weekends.
He had cool hair.
E equals MC squared. E equals MC squared. E equals MC squared. E equals MC squared.
He's known for being really smart.
Okay. Who said white light was made up of the color of the rainbow?
Newton.
Newton did that. Who made a periodic table but they didn't accept it?
Meyer.
Who made a periodic table that they did accept?
Mendeleev.
Mendeleev.
This pronunciation count.
Did you find it?
What? Yep, I did. I found it. Okay.
Who had it?
So,
Mr. Thompson.
who had the Crookes tube?
Oh, Melville. Melville went down, right? Melville.
This is the Tesla coil. Creates an electric current. That's what happens when you shoot it through a Crookes tube.
Wait, do the other side.
And if you have a magnet, you can get that beam of light to react to a magnet, which means there is a relationship between electricity and magnetism, ladies and gentlemen.
What if you put your tongue on that?
What if you put your tongue on that? Come on up. Sit down. Jeez. I'll go get the bed of nails for you, the starter kit instead.
Oh, that might feel good.
Right?
I was gonna say, put it on my bag.
You'll only do it once.
No.
So they found that there was a relationship between electricity and magnetism.
Why is it green?
Why is it green? Because that's the color of the gas inside what it emits. Different gases would do different colors.
So can we do
It's- Do you have a Crookes tube with a different gas in it? Because I had a hard time finding this one. So, okay. So there you go, ladies and gentlemen. Anybody we missed? Anybody on there who we missed?
Mosley
Mosley, what? Okay, come on, Mosley.
set up the current periodic.
Found the proton and modified our current periodic table to be based off of the atomic number. Anybody else we missed? Democritus started the idea of the atom, discontinuous theory of the atom, meaning there's some small piece that can't be divided up. Bohr, we did say energy levels.
Dobringer and the
Dobereiner,
the triads.
he did triads. He didn't actually he didn't create a periodic table, but he started to set up groups of elements based on similar properties and things. And then, anybody else?
Dalton.
Mr.
Did we do Proust? We did Proust. Proust was the law of definite proportions. Definite proportions.
Do we do Pauli?
Pauli. Oh, good. Pauli and Heisenberg. Pauli, what did he say?
Exclusion interval?
What does that mean?
Something about exclusions.
No two electrons are the same.
No two electrons have exactly the same four quantum numbers. Every electron in an atom has its own unique set of quantum numbers. What was Heisenberg?
Uncertainty principle.
Which is what?
Predict place or how fast.
You can either predict the place of an electron or how fast it is moving. Good. Questions? Okay. We are flying, ladies and gentlemen, because we have to be done by the end of this week. Because next week, Monday and Tuesday, I want to give you time to take practice tests. Okay? Those are worksheets 7, 8, 9, and 10 in your packet. Okay? Now, I have not written anything down on the board as far as worksheets that are due. Why? Because I'm not collecting them. But it would do you wise to look those worksheets over. And we're going to talk today about periodic trends. And there is a worksheet on there that says, okay, which of these two metals is more reactive? Which of these two elements has a higher ionization energy? Which of these two elements has a higher electronegativity? Now, you may not know what that means now, but you are going to. And these are trends in the periodic table. And we talk about trends, we're going to talk about trends two ways. We're going to talk about trends that go across a period. We're going to talk about trends that go up and down a family or a column or a group. JVB, what?
Are we going to need our solubility chart?
No, not for this test.
Okay.
No. Okay? But you will need your periodic table. So let's take out the periodic table, ladies and gentlemen, the one that looks like this with all the blanks on it. Not just some, but the one with all of the blanks. Not the one where there are columns going up and down the rows. This one that I had given you. Okay? This one that I had given you. Okay? We have put nothing on that yet. That is about to change right now, ladies and gentlemen. Oh. Blue, orange, or burgundy? Blue it is. Blue it is. Teal blue or light blue?
Light blue.
Good, we'll go with light blue. All right, here we go, ladies and gentlemen. All lefty. So, some important elements to put on there, some key spots on the periodic table that we are going to be using. Let's begin up in group 1, period 1. Lightest element. Lightest element. Okay, lightest element. Group 14, period 2, carbon. Basis, and I know we wrote this on our other one, for life on this planet. Carbon is the basis for life on this planet. By the way, because you are carbon-based, ladies and gentlemen, you have two possible futures ahead of you, ladies and gentlemen. Two possible futures. Anyone know what they are? I was thinking beyond that. Your two possible futures are writing utensil or diamond. I, ladies and gentlemen, if I choose to die, which I plan on not doing ever, will be a diamond someday. You may be graphite. That's the writing utensil. Okay? Sorry, those are your choices. All right. Let's get this crap out of the way. Period 7. Down at the bottom, starting in group 13. Sorry, we're close. All the way to group 18. Those are the man-made elements, ladies and gentlemen. So if they talk about elements that are man-made, those are the ones they're talking about, because everything 92 and earlier is a naturally occurring element. Well, 92 occurs down here in the actinides in the 7th period, so it occurs somewhere in here. Now again, this section of the periodic table is not part of what we have on ours, but these elements here, which are man-made, are on that periodic table for you, just so you know. Okay? These are man-made. These are not natural. They are created by us in a laboratory somewhere. Good. Questions? Okay. So now, in period 4, in the second and third, or group 2 and group 13, even though these elements are right next to each other, they differ by 11 in atomic number. Because we have eliminated this portion of the periodic table here, calcium has an atomic number of 20, gallium has an atomic number of 31. So even though on our periodic table, on this one, on the one you will be using on your test, those two elements are next to each other, they differ in atomic number by 11. So do the ones right below them. So in period 5, that same thing happens. They differ by 11 in atomic number. And when we go down to 6 and 7, they differ by 25 in atomic number. Questions? Group 17, period 4, is one of the two liquids on the periodic table. That is the spot of bromine, ladies and gentlemen. Bromine is a liquid at room temperature. The other liquid at room temperature on the periodic table does not exist in this periodic table because what element is it? Mercury. If you want to know the states of matter, ladies and gentlemen, you need to look up to that periodic table above your heads. If the element is in red, that means that it is a gas. If it is in blue, that means it is a liquid. And if it is in black, that means it is a solid, which means most of the elements on the periodic table are solids, ladies and gentlemen. Questions?
Why are there not many liquids?
Because to be a liquid on Earth is a very small range of temperatures. Things that are colder than this are solids. Things that are warmer than this are gases. Most of the things on there have a melting point when it will become a liquid that is much higher than room temperature. Most of the things on there that are gases have a boiling point that is much lower than room temperature, which is why they are already boiled in a gas. So Just happens to be. Questions? Okay. Now, today, as we are going through some things, ladies and gentlemen, I am not going to write everything down for you. You decide what you want to write down. Now, if I were you, I would have your computers open so that you can be on the slide I'm on, so that as I'm talking about things, you will know what I am talking about. But this is the periodic table that you are going to use the most today, because we are going to talk, we'll occasionally use this one as well, but we are going to talk about trends that happen within a family and also that happen within a row going across the periodic table. So a trend is something that goes up, goes down, stays the same. Okay? We will be talking about those, and everything that we're talking about today will be on the periodic table. Yes, sir. Do I have another one of these? Yes, Stephen. I have yours, as a matter of fact, because I set it aside for you, and here yours is, sir. You bet. So, all right. Are we ready to rock and roll, ladies and gentlemen? Okay, we'll take absolute and utter silences. Yes, Mr. Brand, we are ready to go. All righty, ladies and gentlemen. So, here we go. Go we shall. All right. So, we are talking, ladies and gentlemen, about periodic table trends. All right. So, first of all, the periodic table is divided into two sections. What are they? Metals and nonmetals. Okay? Metals and nonmetals. Metals are on the left-hand side. Nonmetals are on the right-hand side. What does it mean to be a metal, ladies and gentlemen? Metals are ductile. That means they can be drawn into wire. Now, I am not going to, on your test, ask you to define what it means to be ductile. I'm not going to ask you on your test to define what it means to be malleable. But I may say this element that is very ductile and malleable is in the third period somewhere, and you should know that I'm describing a metal. Go ahead.
If, for example, if ductile or malleable comes up on a test and we ask you, what does this word mean? Is that something you can tell us or something you can't tell us?
Sure, I could tell you.
Okay.
There's only one test left, you know, right?
I know, but...
Good. Excellent. Malleable means that it can be pounded into sheets. Oxidized in redox reactions. Metals are oxidized in redox reactions. They are good reducing agents. They lose electrons. They are shiny, or the term for that is they have luster. They have high boiling points, which is why most of them are solids. Nonmetals are the exact opposite, ladies and gentlemen. Nonmetals are not ductile. They cannot be drawn into a wire. They are not malleable. They cannot be pounded into sheets. They get reduced in redox reactions instead of oxidized. They are good oxidizing agents instead of good reducing agents. Metals lose electrons. Nonmetals gain electrons. Metals are shiny. Nonmetals are dull. No luster. Nonmetals have high boiling points.
Nonmetals have low.
I think I said that wrong. I'm sorry. But that was very nice coordination. Very nice. By the way, what does it mean to be not ductile and not malleable? We have a term for that. We call it brittle, which means it will simply break apart. Break apart. Questions, ladies and gentlemen? Anyone need more time? I can move on. Okay. So properties of the periodic table, ladies and gentlemen. The most reactive metal on the entire periodic table is francium. Take this periodic table, the one we were just working on, ladies and gentlemen. The one we were just working on, francium, is in group 1, period 7. Most reactive metal. That is the spot of it. The most reactive metal. Now, we have just finished talking about the properties of metals and nonmetals. How do those properties compare to each other, ladies and gentlemen? They are opposites. So therefore, if in the lower left-hand corner is the most reactive metal, where is the most reactive nonmetal? What element? Is in the upper right-hand corner right there? No, that's not the upper right-hand corner. Phoebe, I know very little, but I know upper and I know right hand.
It's diagonal. Okay, no, not like that.
This is the lowest left spot. Where is the highest spot on the right?
217.
What?
Oh my gosh.
Why not 218? Or why not 118?
A noble gas moves. It's a noble gas.
So? Is it a nonmetal?
Yeah.
So why isn't that the most reactive nonmetal?
Because it's unreactive.
Thank you. Good point. It's unreactive. Unreactive metals, nonmetals won't react. So therefore, the most reactive nonmetal is fluorine. Good job.
Like that's what you put on your teeth. Yeah.
Most reactive nonmetal. So what that means, ladies and gentlemen, is if you get closer to this spot, you are what as a metal? Now again, remember, we would make a comparison within a column, group or family, or within a row. Okay? It would be unfair for me to ask you to compare one column and row to a different column and row. We would have a hard time doing that. Especially if we were to do something like this. Right? If this is the one you're comparing, we know this one will be more reactive, correct? Because it's closer to here. If you're comparing these two, we know the one on the bottom will be more reactive. But if we do something like this, we have difficulty telling. So I won't do that to you. I won't make you compare things that aren't in the same family or aren't in the same period. Question.
In that example, what is closer?
What do you mean?
So if it's like 5, like if they are.
Well, here is the fact. This family is far more reactive than this one. So even this one down here is not going to be as reactive as this one up here. Because this family is just far more reactive. Far more reactive. Questions? Good. Good. So again, we just said this. The most reactive nonmetal is fluorine. You cannot count noble gases in a reactivity trend because they are not reactive. That's why we take them out. Okay? Atomic radius. What is atomic radius? Okay, I was hoping you wouldn't read that to me. What is it? What is a radius?
Half the distance of the circumference of a circle.
Okay, and what do we expect the shape of an atom to be?
A circle.
That's what we normally represent it as, a sphere. Okay? So atomic radius is how big the atom is. Simply put, it's how big the atom is. Okay? Now, it is half the distance between two covalently bonded like atoms. That's the technical definition of it. I'm not going to ask you for the technical definition. But the clue may be orange and yellow, or orangium and yellowium are right next to each other on the periodic table, even though they differ in atomic number by 11. Now we know where they differ in atomic number by 11. Where? What? 2 and 13 in period
4 and
5. So somehow I got to get you into period 4 or 5. They're in the same period as the number of d orientations. 5. 5 d orientations because there are 10 d electrons. 5 d orientation. 5th period right next to each other, right? their radius, atomic radius, the larger atomic radius has a higher frequency. Orange and yellow, which one has a higher frequency?
Yellow.
Okay, I got both answers. That's good because those were two choices. What happens to frequency as you go across?
We get more reactive.
What happens to frequency as you go across that electromagnetic spectrum?
The closer to the right, the higher the frequency.
The further to the right, the higher the frequency. So in Roy G. Biv, which one is further to the right? Orange or yellow? Yellow. So yellow would have a higher frequency. It would have a larger atomic radius. Well, let's find out what atomic radius does. As you go down a period, atomic radius decreases. So ladies and gentlemen, on the one where it is here, this table, you may want to, I'm sorry, I'm not showing you this. I don't know how you're going to do this, but you may want to put down that atomic radius as you go down a period, increases. Wait, atomic radius decrease. Shut up, I'm dumb. I'm not reading what I'm writing. As we go across a period, I'm sorry, I was showing you down a row, which is why in my mind it didn't make any sense. Atomic radius decreases, meaning the atom gets smaller. The atom gets smaller. So somewhere on here you want to do atomic radius and then going across decreases. So all of our trends for periods, we're going to talk about going from the left-hand side to the right. Okay? From the left-hand side to the right. And the atom actually gets smaller. Now, in the back of the room over there, I have a big yellow periodic table which shows you the size of the atoms. But they basically get smaller, ladies and gentlemen. Summarizing it really quickly, here's why. The electrons in a period all go into the same energy level, correct? So electrons in the second period all go in the second energy level, right? And yet the atom gets smaller the more electrons you put in. Why? The only reasonable explanation that we can give you is electrons are attracted to what? Yes, good, the nucleus, because that's where the positive charges are. So as the nucleus becomes more and more positively charged as you go across a period, it pulls all the electrons closer to the nucleus. It makes the atom smaller. It makes the atom smaller. Okay? But now, ladies and gentlemen, if we are going down the family, electrons, which make up most of the radius, go where when you go down the family? When you go from the second member of the family down to the third, where do the electrons go? To another level outside, right? So what's going to happen to the radius?
Expand.
It's going to get bigger. So as we go down the family, atomic radius actually increases, which means your larger atoms are where? Larger atoms are where?
At the bottom.
At the bottom. Smaller ones are at the top. But when you're talking about going across a period, the larger ones are to the left, smaller ones are to the right. Questions? Now there is something called an ion. Go ahead.
So the larger atoms isn't determined by its mass.
No, because in a way, yes, but no. The size of an atom is mostly determined by the electrons around it. Okay? The size of the atom is determined by the electrons around it in the electron cloud. Now, again, as you go down the periodic table, the atoms are going to get more massive, and therefore they get bigger. But the reason they're getting bigger is every time you go down a period, you add an energy level that makes the atom bigger. It goes on the outside. As you go across the period, instead of down them, as you go across the period, more electrons are put into the same energy level, but more protons are put in the nucleus, and that pulls the electrons closer to the nucleus. That's why it gets smaller as you go across. Okay? Now, ionic radius will be a little bit different. Why? Because an ion is a stable ion. So the radius of a stable ion. So what kind of ion does sodium make? Come on, sodium. What kind of ion? Okay, what kind? What's its charge? +1. It's going to gain 1 electron. What's magnesium going to do? Gain 2 electrons. What is aluminum going to do? +3. Because they're doing what with their electrons? To become a +1, a +2, a +3. You are losing electrons. When you lose electrons, 1 electron is lost by sodium. How many electrons does it have then? Instead of 11, it has 10. Magnesium loses 2 electrons. Instead of 12, it has. And aluminum loses 3 electrons. Instead of 13, it has. Which is why they are all isoelectric to what noble gas? Neon, the noble gas before them, correct? Okay, so thinking what we just thought, as you go across, okay, you have 10 electrons, whether you are sodium, magnesium, or aluminum, because you are a stable ion, correct? In the nucleus, though, you have 11, 12, and 13 protons. What's going to happen to those electrons as you go across, even though they're in the same energy level? They're going to decrease. They're going to decrease until something happens. Until we get to silicon. Because silicon is no longer going to lose electrons. It is going to what? Gain. How many?
4.
And it's going to look like what?
18.
Argon, not neon. Phosphorus is going to gain
3.
and look like argon, not neon. Sulfur is going to gain
2.
and look like argon, not neon. And chlorine is going to gain 1 and look like argon. So how many electrons does silicon have?
14.
Try again.
Oh, wait. Oh.
When it becomes stable, it has 18. How many does aluminum have? 10. Those 10 electrons are in what energy levels? But silicon right next to it has how many electrons?
18.
Which are in,
Second.
so which one's bigger?
Silicon.
The nonmetals in the same period are going to be bigger than the metals in the same period as ions. So as you go across through the metals, the radius is going to go down. But when you jump to the nonmetals, what will happen?
Go up.
It will go up 1 time. 1 time. So through the period, the ionic radius is going to go down. However, when you get to the nonmetals, it will go up and then start going down again. Why? Because instead of losing electrons and going down to a lower number of energy levels, you start gaining them and having 1 more energy level. Questions? That is an important difference, because a question that asks you about atomic radius and one that asks you about ionic radius get a very different answer. So it is possible for 2 atoms to be next to each other and one have a larger atomic radius, but it could have a smaller ionic radius. But the only way that is possible is if those 2 elements, one's a metal, one's a non-metal. One's a metal, one's a non-metal. Okay? What happens as you go down the period or down the family? It still goes up. Ionic radius and covalent radius doesn't matter. Ionic and atomic both go up as you go down the family, ladies and gentlemen. As you go down the family, they both go up. Questions? Electron affinity, what does that sound like? If you have an affinity for something, what does that mean?
How you affect something.
What?
How you affect something.
Not infinity, affinity.
How you affect something.
How you affect something. Affinity is what you kind of like. Electron affinity, ladies and gentlemen, is the ability to attract and hold an extra electron. What kind of atoms suck at this?
Hydrogen and helium.
Nope. Well, you are right about one of them. What kind of atoms do not want to attract and hold an extra electron? Noble gases. Why? They're already stable. Now, after them, what other kind of atoms don't want to attract and hold an extra electron? Nope. Nonmetals would love that. Because nonmetals are trying to do what with electrons? Gain them. Hey, you give a nonmetal an electron and say, woohoo, I'm a happy boy. Ain't giving this sucker up. Nope, no way. No way, I'm closer to being stable. Metals don't want that. They'll do that. Metals, get rid of them. What element has the highest electron affinity? What element has the highest electron affinity? Ability to attract and hold an extra electron.
Fluorine.
Bingo. Fluorine. It gets one more, it's stable. Give fluorine one electron. You ain't getting it back, son. Nope. I'm keeping it. It wants an electron, it will hold on to it. So as you go across a period, electron affinity actually goes up. Why? Because you're going from metals to nonmetals. You're going from elements that don't want an electron to elements that do. Electron affinity increases as you go across the periodic table. So then what happens as you go down?
The opposite.
Which would be?
They want to lose them.
No, not necessarily. But fluorine really wants an electron. And it does a great job of holding on to it. Why? Because when fluorine gets an electron, that electron is very close to the nucleus. Chlorine wants an electron too. It grabs it, it holds on to it, but it can't hold on to it as strongly as fluorine can. Why?
Not as close to the nucleus.
Not as close to the nucleus. So even though chlorine wants to hold on to it, it can't hold on to it as strongly as fluorine can. So as you go down a family, electron affinity decreases. Decreases. It's not that they don't want it, they just can't hold on to it as well. Because if that electron becomes further away from the nucleus, it is harder to hold on to it. Questions? So again, ladies and gentlemen, if I give you a clue that gets you into a period, okay, gets you into period 16, and it says this element named after your great chemistry teacher in class has a high electron affinity in group 16. Where is it going to be in group 16? Near the one. Which is where?
Oxygen.
Near the top. If it has a low electron affinity, it would be near the bottom. So again, getting you into an area and then telling you where in that area it is. Boom, there you go. All right. Electronegativity, ladies and gentlemen. Electronegativity is the tendency of an atom to attract electrons to itself when combined with another atom. Okay, what kind of atoms like to do this? What? So francium has a tendency to attract an electron to itself when combined with another atom. Francium wants to do the exact opposite. It wants to do what with an electron? Get rid of it. So therefore, electronegativity as you go across a period increases. Why? Because you go from atoms that want to get rid of electrons to atoms that want to gain them. So electronegativity increases as you go across. What would happen as you go down the family? It would decrease. Again, where's the highest electronegativity? The same place that has the highest electron affinity? Fluorine. Sorry, I almost said francium. Fluorine. Questions? So, well, you are not reliant on understanding the definition here. If you understand the definition, you can figure out what elements have good electronegativity. Metals do not want to attract an electron to themselves. They want to get rid of them. Non-metals want to attract an electron, so they would have a high electronegativity. Ionization energy, ladies and gentlemen. What does that sound like? Okay, to become an ion, you need to do what? Really? Come on. To become an ion, you need to... What? Nope. Nope. No, it doesn't have anything to do with energy directly. To become an ion, you need to...
Something like that.
gain or lose an electron, which will cause you to combine. Okay? So ionization energy is the energy needed to remove an electron from an atom or ion in its ground state in the gaseous phase. Meaning, I'm going to take an electron away from you. Okay? I'm going to take an electron away from you. Now, which family would you have the hardest time getting to give up an electron? Noble gases. Why? Because they're stable. They're stable. You want to take an electron from the noble gases, bring a truckload of energy, ladies and gentlemen, because that's the only way they're doing this. You can force them to. They don't want to. Go.
What does it mean when it's ground state?
Meaning,
gas phase?
ground state means that it is in its lowest energy state. No electrons have been promoted. We haven't added or gained any. Lowest energy.
Just as is.
Just as is. The noble gases, you would have the hardest time giving them to remove an electron from, because they are already stable. What family has the easiest time removing an electron from? Removing, giving away. The alkali earth metals. The alkali earth metals. Okay? The alkali earth metals. So as you move across a period, ionization energy increases. Why? You go from atoms that are trying to remove an electron to ones that don't want to remove one. Ones that want to gain to ones that are stable and are like, ain't happening. Nope, can't do it. You can't have it. No. Which means as we go down a family, ionization energy should. Why? Why is it easier to get an electron from francium than it is from lithium? Because it's farther from the nucleus. Good, we're seeing a theme. We're seeing a theme. It all has to do with structure, ladies and gentlemen. All has to do with structure. Questions? So lowest ionization energy, francium. Highest? Now we can include the noble gases. Helium. Question? Okay, electron shielding. Electron shielding, ladies and gentlemen, is the reduction of attractive forces between a nucleus and its outer electrons by inner electrons. In other words, the force that the outermost electron feels from the nucleus, they should be what to the nucleus? Electron should be what to the nucleus? Attracted. But, okay. This is going to be awkward. Josie is attracted to Josh. I'm making this up. I'm randomly picking names. Josie is attracted to Josh. But right now, what's in the way? Phoebe and Jaden. Again, making names up. Okay? So, if those two weren't there, the other two could get closer.
Yeah.
That's electron shielding. Well, you may be attracted to that other. Something's in the way. Something that you were repelled by. Josie can't stand this girl named Phoebe. She's repelled by her. Wants to get away. But unfortunately, she's attracted to the nucleus, Josh. So the more shielding, the more layers there are in between, the more electron shielding. So what happens is you go across a period. Anyone?
It's constant. Stay the same.
Why? Because that's what it says on here. And the reason it says that, as you go across a period, how much more is there in between you and the nucleus? Nothing. Potassium is in the fourth energy level. So it has two sets of electrons in between it and the three sets between it and the nucleus, right? How many for gallium? Still those same three sets of shielding. You go across, it doesn't matter. Why? There's the same amount of electrons between you and the nucleus. But as you go down the periodic table, the electron shielding does what? Increases. More people between. We take Josh, we put him over there. Put more people in between. Makes it harder to be attracted to him. Okay? Nothing personal, Josh. I'm not saying you're hard to be attracted to. I don't know. Not claiming anything. Questions? Okay. Oxidizing agents is a substance that causes another substance to be oxidized. Okay. Substance that causes another substance to be oxidized.
Isn't that what happened in sexuality?
Well, that happens when things rust. Yes, they become oxidized. Very good, ladies and gentlemen. Very good. It is what is reduced. Reduction means something has gained electrons. Oxidation means something is losing electrons. Okay? So, if something is reduced, it gains electrons. What would that cause something else to do? If you're going to gain electrons, something else has to lose them. So, if you are gaining electrons and being reduced, something else has to be losing electrons and be oxidized. So, what are good oxidizing agents? The nonmetals, because they are trying to gain electrons. So, the best oxidizing agent is fluorine. Now, you could go back to the periodic table that has all the squares on it, and under fluorine, put best oxidizing agent. Which, by the way, ladies and gentlemen, what does that mean for francium? If fluorine is the best oxidizing agent, francium is the best. The worst oxidizing or the best reducing agent? Francium is the worst oxidizing agent. However, francium is the best reducing agent. So what would be the worst reducing agent? Fluorine. And again, as you get closer to them, you would get worse or better. Questions, ladies and gentlemen? Do you need more time? Okay, again, utter and complete silence. I'm going to assume that means go, Mr. Brand, go. Go, Mr. Brand, go?
Yes.
Or no, Mr. Brand, no?
Go, Mr. Brown, go.
Go, Pike.
Okay. We are going to briefly talk about nuclear reactions.
Yeah.
Radioactivity is the spontaneous breakdown of the nucleus of an atom that releases energy. All elements 82 and higher are radioactive. What is element 82 on our periodic table, ladies and gentlemen? What is element 82 on our periodic table? Lead. What group is lead in? What group is lead in? What period is lead in? So, from here, every element after that is radioactive, for sure. Every element from here on out, including the seventh period, is radioactive. Everyone is radioactive. And there are two kinds of decays that we're going to talk about. By the way, radioactive decay is unlike any chemical reaction because we are talking about literally changing the nucleus of the atom. We are talking about literally changing the nucleus of the atom. And if you are radioactive and you undergo what is called alpha decay, you lose 2 protons. That means you literally become a different element on the periodic table. You literally become a different element on the periodic table. So, for example, ladies and gentlemen, if polonium underwent alpha decay, it would lose 2 protons and become what?
Lead.
It would become lead. What if it lost 2 alpha particles?
HG.
It would become mercury. So anytime you undergo alpha decay, you are going to lose 2 protons per particle. 2 protons. Okay? So you will literally back up 2 spots on the periodic table. Literally back up 2 spots. However, ladies and gentlemen, there is also what is called beta decay. Beta decay, you gain 1 proton. Now, real quick, losing 2 protons is understandable because if your nucleus breaks apart, it can take pieces of it with it. Okay? That's how the 2 protons get lost. They go off, flying away as an alpha particle. An alpha particle is really a helium atom. Why? Because any particle with 2 protons in it is going to be helium. But how do you create a proton that wasn't there before? A neutron in the nucleus breaks apart. And it breaks apart into a proton, and guess what else? An electron. The problem is now there is an electron in the nucleus, and where do electrons belong? Out in the nucleus. Get out, dude. Goes flying out of the nucleus. But it leaves behind 1 more proton than was there. So now, if something undergoes beta decay, bismuth undergoes beta decay, what does it become? It becomes polonium. It becomes polonium. Okay? Certain elements undergo certain types of decay. Yes.
Is that how we created those elements?
No. No. Because we would have to create these elements, they're taking smaller atoms and smashing them together at incredibly hard, fast speeds, incredibly hard. and hoping that they will fuse together. Radioactive decay happens naturally. It happens naturally. And for example, uranium only undergoes certain types of decay, and actually only certain isotopes undergo certain types of decay. We're not going to get into all of that. Okay? We're not going to get into all of that. Okay? Now, that is what we have here. We're not going to worry about gamma decay because, to be honest, gamma decay doesn't change anything. All it does is give off energy. Doesn't change what it was. Okay? There is, however, an old prefix Eka. And Eka means one below on the periodic table. You remember yesterday we were talking about the story of Mendeleev and how he left blank spots on the periodic table? Okay? Well, one of them is the spot where gallium is right now. That was an element that was not discovered when Mendeleev had set up his periodic table. So to put something in that spot, when they first discovered gallium, they called it Eka aluminum. Eka means one below on the periodic table. Okay? Eka means one below on the periodic table. I would write that down. That would make a great clue on the test. Artium used to be called fercium used to be called ecabranium. Where would ferc have to be? What?
Underneath.
Well, where would branium have to be, though? Right above fercium. I don't know. It depends on which one you're trying to place, doesn't it? Which one's already on there? Okay, so again, that Eka means one below. Maybe it's not referring to the one below. Maybe it's referring to the one above because fercium is already on there. I don't know. We'll see. We'll see. Going to be interesting. Going to be interesting. Okay, time to blow minds a little bit here, ladies and gentlemen. Ionization energy. We did. We did. And we said it was what? The energy needed to what? Yes. How many electrons can you remove? Oh, you can remove many. You can remove many. Matter of fact, you could talk about the first ionization energy, which is the energy needed to remove how many electrons? Just one. What family doesn't mind giving up one electron? Alkali. What family doesn't want to give up one? Good. The noble gases. So it is the energy needed to remove the first electron from an atom in its ground state. That is the same definition that we just gave you. Which means the highest is helium in group 18. That's the one you're going to have the hardest time getting this electron from, right? What's going to have the easiest time? It's going to have the lowest ionization energy. Francium. Francium's going to have the lowest. Questions? What if we want to remove a second electron? What group has the easiest time losing a second electron, ladies and gentlemen? Which one? No. Actually, they have the hardest time giving up a second electron. You know why? What happens after alkali gives up one electron? Just like the what?
Noble gases.
So why would they give up a second? They wouldn't. They finally got rid of one like, woohoo, I am stable. Yes, what I've always wanted to be. Quick, give me a second electron. Hell no, go away from me, dude. I'm stable. Which ones? The alkaline earth metals. Why? They want to give up 2 electrons. They gave up 1. They're closer to being stable. Please, take 1 more. Take 1 more. The energy needed to remove the second electron, the lowest is, or the highest would be group 1 now. Why? They become stable after losing 1. They're not giving up another one. And what's the lowest? Group 2. Now wait, we're going to see a pattern. We're going to see a pattern. What about third ionization energy? Energy to remove a third electron. What group has the hardest time giving up a third electron?
Group 13.
No. They actually have the easiest time. Here you'll notice helium has the hardest time giving up the first electron, right? Group 18. Then it comes group 1. What's next?
Group 2.
Group 2. Why? Because after losing 2 electrons, it became stable, didn't it? You think it wants to give up a third? Hell no. Not doing it. You can't have it. So what group has the easiest time giving up a third? Okay, group 1 had the easiest time giving up the first. Group 2 had the easiest time giving up the second.
13.
Group 13 has the easiest time moving up the third. Guess what's happening, ladies and gentlemen? Our trend is just doing what?
Left or right.
Sliding one spot at a time. What would have the highest fourth ionization energy? Group 13. Highest, group 13. Lowest would be group 14. And it would just keep moving and moving and moving and moving. Questions? Understand why? Makes some sense? This is the most logical unit you will ever have in here, ladies and gentlemen. Seriously, it is. Need more time? This, ladies and gentlemen, is what we've already got on our periodic table. But this is what is called the Lewis structure. The Lewis structure shows the electrons around the nucleus, only the valence ones. Only the valence ones. Lithium has 1. Beryllium has 2. We went through this. This is the top thing we put on there, right? Group 2 has 2 valence electrons. Group 3 has 13. Group 4 has 4. Group 5 has 5. Group 6 has 6. 7 has 7. 8 has 8. Correct? Yes? 2s1, 2s2, 2s2, 2p1. Why are there 4 separate here? It took one of the 2 S's and put it into a 2p so that they could all be separated. Doesn't always happen. Happens with carbon though. 2s, 2p1, 2, 3. 2s, 2p1, 2, 3, 4. 2s, 2p, 2, 4, 5. 2s, 2p, 2, 4, 6. There's your electrons, ladies and gentlemen. Outer shell ones have to be in the S's and the P's, right? Good, good, good. Excellent, wonderful. Questions? Come on, what are you sitting there for? Let's go, come on. Come on. Leave your computers, bring your bodies. That's all I need. Maybe mine would be appreciated. Maybe you're going to be my van. Good. See that periodic table over there? Go point to the element magnesium. Okay, there's magnesium on the periodic table. What period? Second period. What group? What group? Alkaline earth metals, but what group? 2. Good. All right, come on back. Okay, ladies and gentlemen, we are going to take some magnesium and we are going to mix it with water. This, ladies and gentlemen, is called phenolphthalein. Phenolphthalein is an indicator that does some cool stuff with water. You're going to see what it does in a minute. Right now, what does it do? Not a dang thing, because it doesn't react with water. Okay? So now what I'm going to do, ladies and gentlemen, put some phenolphthalein into all of these, because I'm going to be using these in just a minute. But phenolphthalein doesn't do anything when you put it into water, until, ladies and gentlemen, you decide to add something like magnesium. So we're going to take and we're going to add a little bit of magnesium to this water with phenolphthalein, ladies and gentlemen, and we're going to see if there is a chemical reaction. Ready? 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 Is there a chemical reaction? You sure? Well, then get your butts closer to it.
No, I'm scared. What if it that?
If it's going to boom, I wouldn't tell you to get closer to it. Is there a reaction? No! Get your butt closer to it! Tell me what the reaction is. I see it. Nobody else does? What color is it changing to? It's changing to purple down by the metal, isn't it? Now you're like, oh my God, you mean he's making me actually look at it? Is it turning purple down by the water?
That's purple.
You bet it is, ladies and gentlemen. Is that reaction happening very quickly?
No.
Is that a strong reaction with water? No. Go point calcium. Where's calcium compared to magnesium? Echo lower. Right below it. Same group. Different period. Let's put some calcium in water, ladies and gentlemen, and see what happens. You ready? You ready? You ready? You guys don't seem like you're ready.
I'm like SpongeBob. You ready?
That's disappointing, ladies and gentlemen. That's disappointing. Hold that thought. Gotta hurry, gotta hurry, gotta hurry.
And with the shit to with the whole thing.
Oh, that was fast. I got minutes to spare. All right, let's try this again, ladies and gentlemen. That's better. More or less reactive? More. Good, 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 good. All right. Go find me sodium. Actually, sorry, lithium. Excuse you. Lithium, what family? Alkaline. Where? What group? Or, I'm sorry, what period? 2. Nope. Yep. Here's lithium, ladies and gentlemen. There's lithium. Okay? Let's take and add it to water and see what happens. And what happened, ladies and gentlemen? Give it a second.
Oh, it sounds squeaky.
I don't know how you guys can see a damn thing from back there, but okay, if you want to stay back there and not get near the excitement, go ahead. Tell me what's happening.
Pink and it's bubbling.
More pink than those?
Yes.
Yeah. Tell me what you notice about it. It's giving off a, starts with G, ends with, never mind.
Gas.
Thank you, gas. More or less reactive than those? More, good, good, good. Find me sodium. Sodium is below lithium. What happened when we went below magnesium? More reactive. Good. Good. We want more reactive, ladies and gentlemen. Now I got a tiny little piece of lithium here. So let's take, I really need, oh man, I'd love to throw that in there all at once, but I don't feel like evacuating the school today.
Why? It's nice outside.
Is it?
Yeah.
Is it really? Well, I don't want to be the next person on the news for the district. Let's put it that way, okay? All right, so let's see if this is more reactive than this last one. Okay, you ready? You ready? You ready? You guys don't seem like you're ready. You just don't seem like you're enjoying this. Maybe we shouldn't even do it. But we're going to do it anyway. What else? Where'd it go? That's it?
Oh, you
That's
should put that
it?
whole piece in
We
there.
got to put a bigger piece in there. That ain't going to cut it. Was it more or less reactive? Yeah, I think so. I thought it was more reactive. I just heard this popping sound behind me, and I'm like, what the heck happened? Phoebe screamed a little bit, and I was all nervous.
That was, remember, that happened with the can thing too, where I did it and he was like, no, you're.
Yeah, all right.
Last try that.
All right, let's try this. Maybe this will go longer. Here we go. Here we go. More or less reactive? I would say more. I would say more. You're scared it's gonna pop? Boom!
Why is he so ready?
You guys are all leaving. The best is yet to come.
Dave asked by the way, he's gonna have to stay keeper for a little bit. I think we should have put the whole chunk in there personally.
Personal album.
I guess we'll have to finish tomorrow. Or we can just say, forget about it, let that
No,
stay.
let's do that tomorrow. But I think you should just put the whole chunk.
Have a good day, ladies and gentlemen. Get out! Go away! Go! Get! I'm gonna be here after school today, yes. Okay, that's why I'm here. Okay? I will be more than happy to help you. Thursday, we don't have to stay late on Thursday.
Wait, you're leaving, right? But it's a
Come
Friday.
tomorrow, because Thursday is our Friday this year. You're gonna make me stay late on the day that I get out of here early? Come in on Wednesday. Hey, what are you doing?
Why is there still a password, Christopher?
Get.
Oh,
Well, who is it from? Or who is it? What, did you ever end it when you got here?
Exactly right away.
I don't know. Did you get it when you got here from your last class? Get out of the way to let intelligent students come in and out of the room.
Hello again.
Hello!
Was that necessary?
Yeah, I think so.
Oh, darn it. 9:15.
I also don't feel like I can do this throughout. Or math. I never watched River After High School. We were talking about it last night.
I didn't watch anything as kids. because I've been a dinosaur trainer since. But I started memorizing and regurgitating ads word for word, like the entire 1 minute long ad, word for word.